So guys, we are in the last part, probably, of equilibrium of forces. Equilibrium of forces. That's like equilibrium in solids, of course. So we are now in that part called the moment of a force. So I will start off by explaining the theoretical aspects of this section. So how will I even explain? So remember that we all open doors, we all turn taps, we all ride bicycles. Not all of us ride bicycles, but I'm sure that most of us, we all turn taps. So if you want to switch on a tap, you apply a certain amount of force. But that force produces a turning effect. It produces a turning effect. Same thing too when you open a door. You open a door. When you're riding on a bicycle, it produces what? It produces what? A turning effect. So, if we're looking at this case now, we have two things involved. We have the force applied because you apply the force, and also we add a turning effect. That means you applied a force at a certain distance. So, if I'm to give you the simple definition of what a moment of a force means, it means what? The product of what? Of a force in its what? In its applied what? Is applied what? Is applied distance. Understand? Moment of force what? In its applied distance. So the moment of a force is the turning effect of that force about that point. I can't draw a tap. I can't draw a door. But what? The moment of the force, what is the turning effect of that force at that what? At that particular point. So if you are turning this thing, the moment of this force, the moment of a force is what? The turning effect, the moment of a force. That means if you apply a force to maybe a door or a tap, the moment of that force is the turning effect of that force, and is given as what? As the product of the force and the perpendicular distance of its line of action. Remember, is what? The product of the force and the perpendicular distance of its line of action, not just the number of times the tap turned, or the number of times the door opened, or how many times you rode that bicycle. No, the perpendicular what? Distance of its what? Of its line of what? Of action. So for example now, let's take this for example. Let's say this is a switch, and this is for you to like close the switch. You have to bring it down like this. Now, if you turn the switch down like this, you want to off it. There is a certain distance from here to here, right? And you applied a certain amount of force. So the moment of the force is what? The force applied times the distance of the line of action, of the line of what? Of action. That's what basically the moment of a force is explaining. So basically, if we are taking basic calculations on that moment of a force, we just say what? Moment of a force is equal to what? The force times what? The distance of the line of what? Of action. Force times distance. It's that simple. But where it gets kinky is when we start looking at what? Moment of a force on another level, where we now have what? Principle of movement. We have what? Principle of movement. So let's look at a scenario. I'm sure you'd have encountered this before, but you'd have seen cases. When I put this marker, I've seen cases like this where you have an horizontal ruler or a horizontal bench where you have a pivot in the middle. You have a pivot in the middle, and to make it balanced, they maybe add a certain amount of weight here to draw it down, and to counterbalance it, they have what? Another weight at a distance from here. And the distances are what? They are calculated what? Distances. So if you set up a ruler like this and you add two masses at certain distances from the equilibrium position, they will be at what? At equilibrium, depending on how you arrange them. So if they are at equilibrium, they will be at equilibrium if you arrange them well. But if you remove one of them, they will what? They will not be what? At equilibrium. And I think, not even I think, I know that this mass will what? We drag it down. This mass will what? We drag it down. So the principle of moment says that the sum of what? Of clockwise moments must be equal to the sum of what? Of anti-clockwise moments when an object is in what? Is in equilibrium. Let's stop it for now. I go recharge. So what I stated just now is called what? The principle of moments, where the sum of clockwise moments must be equal to the what? The sum of anti-clockwise moments when a body is what? Is in equilibrium. So let me just explain for you. So now, if you know, I said initially that there are two masses here, and of course they have a weight they are applying. So if this body, which is this ruler, is in equilibrium, that means the sum of clockwise moments, this is a clock. So this is like this is clockwise, right? Why going the other way around is what? Anti-clockwise. So the sum of what? Of clockwise moments. This is telling you that if we remove this box here, this mass here, or this box here, we pull this ruler in this direction. You get like this direction. So if it is pulling this ruler in this direction, it is what? Applying a force in a particular what? Distance in its line of action. That means there is a moment here. And this moment is what? Clockwise. There's a moment. This thing is what? Is the force. Applying it what? In this distance, producing a turning effect. Producing a what? A turning effect. So that is called what? A moment of a force. So this is like a moment, but it's what? It is clockwise. So we call this what? The clockwise moment, because it's what? Is going in the direction of a clock. The what? The clockwise moment. While this one, if this one was the one that was removed, it what? To what? Form the what? The anti-clockwise moment. So this is the direction in which these two will tend to act if they want to disrupt the equilibrium. But the principle of moment says that for this body to be in equilibrium, the sum of clockwise moments must be equal to the sum of what? Anti-clockwise moments. Do you understand? So that's what the principle of moment says. The sum of for a body to be in equilibrium, the sum of clockwise moments must be equal to the sum of what? Of anti-clockwise moments. So it's that simple. So through this principle, we can determine the weight of we can determine the mass or the weight of unknown objects. For example, if I know the mass of this object to be 10 kilogram, and let's say I don't know this one, unknown, let me put M here. So based on that principle, if I'm very, very sure, if the clockwise moment CW is equal to the what? To the anti-clockwise moment ACW. This is clockwise moment, anti-clockwise moment. So if they are equal, I can be able to calculate the mass of this unknown what? Of this unknown object through what? This principle. And also in the principle of moment, the sum of upward forces must be equal to the sum of what? Of downward forces. Or better still, the sum of any force acting in one direction must be equal to the sum of the other force acting in the opposite what? Direction. For instance, now, if we have this ruler, this marker is not given. If we have this ruler and we put masses here, like 2 kg, just 2 kg, and they are acting downwards, of course, they are acting downwards. So this is a downward force. The upward force that is making this ruler to stand must also be equal to the what? To the downward force. So the upward force can be applied by this. You understand? So in principle of moment, the upward forces must also be equal to the what? To the downward forces. Not really upward or downward, but most times it's what? Upward and downward. That is, the force acting in one direction must be equal to the what? To the force acting in the other direction, or rather, the sum of forces acting in one direction will be equal to the sum of what? Forces acting in the other direction. If the body is in equilibrium. Remember, principle of moment applies to bodies that are in what? Equilibrium. So that's it. So in principle of moment, a body that is in equilibrium, the sum of clockwise moments must be equal to the sum of what? Of anti-clockwise moments. So I think I've explained what a moment of a force is, what you need to know. So what we'll now do now is we'll now delve into calculations where we can put all these things into what? Into practice. So let's dive into calculations. Very, very interesting. So before I start taking actual questions, let's look at a very, very, brief scenario. So let's say we have a meter rule or a plank, anything you call it. It's not bad. You have it like this, and you have a pivot at the center. So you know that normally, if you put a pivot at the center, it will be unstable. To be finding, you understand. So to balance it, it's either you put it at the center of gravity, which we'll talk about later, or you add some masses at separate ends to bring it to what? To equilibrium. So let's say we put a weight or a force of 20 Newton here, and we put a force of 60 Newton here. Or even 50. Same thing. Let me put it here. So, and the distance from this point to this point is what? Is A. And the distance from this point to this point is what? Is B. Because, of course, we have a turning effect around this point. So, remember, the principle of moment says that the what? The sum of clockwise moments must be equal to the sum of what? Of anti-clockwise moments. So, this is clockwise moments. This is what? Anti-clockwise moments. So, let's say that. So, moment is what? Force times what? Times distance. So, that's what? 20 Newton times what? Times the distance A. Be equal to what? 60 Newton times what? The distance B. Do you understand? And of course, this body is in equilibrium. So, where this knowledge is very, very important is that if you are given the distance A and you're not given the distance B, you can easily what? Get it. And if you are given distance A and B and you are not given the amount of force or the amount of mass that must be placed here to make this body in equilibrium, you can find it using what? This kind of formula. So we'll see more of this. And note one thing is that there can be more than one force applied to one end. So we can even have like two here. It's not necessarily one. It can be more than that. So let's just put that in notice. So let's take a literal question. Let's take an actual question. Let me take my duster and clean this place. So it's a very simple question. It said a meter rule is pivoted at its midpoint. At its midpoint C with a vertical force of 10 Newton hanging from the distance C, hanging from the distance 30 centimeter rather, from C. At what distance must a 15 Newton force hang to balance horizontally? So this is the question. It said a meter rule is pivoted at its midpoint. So let's draw the diagram. Let's assume this is a meter rule. And what? Pivoted at its what? At its midpoint. This is a pivot. And they call this midpoint, they call it C. Point C. With a vertical force of 10 Newton hanging from the distance 30 centimeter from point C. So we have a 10 Newton force that is what? That is hanging at a distance of 30 centimeter from C. So we can put it here. We can say, okay, 30 centimeter from C. We have what? A 10 Newton what? Force hanging. You're like, at what distance must a 15 Newton force be hanged towards to balance horizontally? So the thing is that at this particular position, this meter rule will not be in equilibrium because there's a 10 Newton force hanging here. So the thing will be going like this. So they are saying that, okay, where should we put this 15 Newton force to make this ruler balance horizontally? So we can't just put it anywhere. We must put it at a calculated distance from what? From point C also to the right hand side, of course, so as it to what? To be at equilibrium. So remember what I said in my previous example. I said that you can be given some parameters to look for the parameters. Like if I'm given the distance of the two forces, I'll be asked to look for an unknown force that will balance it. But in this case, we are given the two forces, but we are given one distance, and we are asked to look for the other distance, the other force will be placed, you understand, to guarantee what? Equilibrium. So how do we do that? Let's call the distance from here to here, let's call it x. Of course, we don't know where we'll put it, but now we shall put the 15 Newton somewhere here. Let's do it like this, 15 what? Newton. So sum of clockwise moment is equal to what? It is sum of what? Anti-clockwise moment. So that is what? 10 Newton times what? 30 centimeter will be equal to what? 15 times what? The distance. We don't know where we'll put it. So we'll put what? We'll put x. So that will be what? X will be equal to what? 10 times 30 divided by what? 15. So 15 here 1, 15 here 2. X will be equal to what? 20 centimeter, of course. Because Newton, you cancel Newton and you have what? Centimeter. So we'll place this 15 Newton at a distance of 20 centimeter from C to what? Make this meter rule to what? To balance horizontally. To balance horizontally. So it's that simple. It's that simple. Let's take more examples. More examples. Many more examples. So this is like the most basic example, and if you get this, you've already gotten a good foundation. We are dealing with calculation under under moment of forces. So I think I have to write these questions down. So you have to pause the video. I have to write down the question. Okay, we read the question the wrong way. A meter rule is found to have balanced horizontally at the 48 centimeter point. That means its initial normal balance point, according to this question, is what? Is 48 centimeter. Then, when a body of mass 60 grams is now suspended at the 6 centimeter mark, the balance point is now found to be at what? At 30 centimeter. So this was the initial balance point. This was the initial balance point when nothing was applied on it, according to the question. So we'll not look at maybe center of gravity or anything. This was what the question gave us, that this is the initial what? Balance point. So we are asked to like calculate the mass of the meter rule. We should calculate the mass of the meter rule. So if this 48 centimeter mark was the balance point, because they said what a meter rule is found to have balanced horizontally at the what? 48 centimeter mark. That means that is its normal balancing point when nothing is added on it. That is telling you that according to this question, this 48 centimeter mark is the center of gravity. The center of gravity for this question though. For this question though. So that's where the weight of the roller we act on. So we are asked to calculate the mass. So we're like, when a body of mass, this is suspended at the 6 centimeter mark, the balance point is found to be at 10 centimeter mark. Calculate the mass of the meter rule. So the mass of the meter rule will be acting at this point, because that was where the meter rule was formed to balance initially. So that is like the center of gravity. So the mass is acting at this point. Of course, the meter rule has a mass, so it's acting at this point, and this mass of 60 grams acts at this point, and they are in what? They are in equilibrium. They're in equilibrium. So we are asked to look what the mass of the meter rule. So how do we do that? We take clockwise, we take anti-clockwise moments, and we take what? Clockwise moments. So what are the anti-clockwise moments? That is just what? 60 grams times distance from year to year is what? It's not 30. The distance, not 60 grams is balanced, it's suspended at 6 centimeter here. So the distance between here and here is 30 centimeter minus 6 what? Centimeter. Because from year to year is 6, from year to year is 30. So from year to year is what? 30 minus 6. Equal to what? M, the mass of the ruler, times what? What is distance between year to year? If year to year is 48, then year to year is 30. Of course, yeah. If year to year is 48, then year to year is 30. Distance between year to year is what? 48 minus what? 30. So that will be 60 times 24 equal to what? N times 48 minus 30 should be 18. So that is 60 times 24 divided by 18 should give you M. So let's solve for that. (60 times 24 divided by 18). The mass of the ruler is what? 80 grams. The mass of the ruler is equal to what? 80 what? 80 grams. So sometimes you have to be careful of unit. You need to wish you are giving your answer, or you are asked to get your answer in. So the second part of the question says that calculate the distance of the balance point from the zero end if the body were moved to the 13 centimeter mark. Calculate the balance point from the zero end if the body were moved to the 13 centimeter mark. So they're now saying that, okay, let me clean this place. If this body was moved to this 13 centimeter mark, that means the distance from year to year was now changed to 13. That means we moved it forward. We moved it forward. So no use drawing a new diagram. Just change this distance to what? To 13. So if year to year is now 13, we should find the balance point from the zero end. So if year to year now was now increased to 13 centimeter, that means the balance point will change. The balance point will what? Will change. I don't draw that image. I would have drawn that image and enlarged it for you, but it's of no use for you. So that means if this 60 gram was carried from 6 centimeter to 13 centimeter, the balance point will obviously change, and that is what we are asked to what? To get. That is what we are asked to get. That's what we're asked to get. So let's get the new balance point. The new balance point. So it's quite simple. We'll take clockwise moment to what? To anti-clockwise moment. So that will be 60 gram times. Now, what is the distance from where the 60 gram is to the balance point? Let's call the balance point X. Should I call it X? Let me call it Y. We call this one Y minus what? 13. So the balance point, we don't know where it is, but we know that the balance point is the distance. The new balance point will be the distance of year to year. Do you get? But this 60 gram is acting towards this moment, towards this point. That means this is the distance between two of them. So to get the distance, we want to do what? Y, which is the new balance point. Y is equal to the what? The new balance point. So why the new balance point? So to get the distance between this place and this place, remember the first time we subtracted, and that was 30 minus 6. But right now, we don't need the new balance point. So call it the new balance point, we call it y. Then this place is now what? Is now 13, because it was what? It was increased to 13. So equal to what? The mass of the roller is what? Is 80, as we got it that time. Is 80 times 48 minus what? Minus x. Sorry, minus y rather. Minus y. Because we want to get the distance between the mass of the ruler where it's acting to the new balance what? To the new balance point. But we don't know it because we don't know the new balance point. So we are looking for that new balance point, which is what? Which is point y. You get? But just go back, rewind back and say how I did the first thing. How I did the first part. I'm just doing the second part the same way. But we are looking for the balance point now. So that is what? 60y minus, what is 60 times 13? That is 780. When you are opening this bracket, that is 60y minus what? 780. We give you what? 80 times 48. To open this bracket, that is 3840 minus 80y. So to collect like terms, you can say 60y plus 80y equal to 3840 plus 780. So this will give you 140y equal to what? Just 780. We give you what? 4620. So to get y, divide what by what? By 140. By 140. That is 462 divided by 14. So the new balance point will be what? Y equal to what? 33 centimeter. So the new balance point will be what? 33 what? Centimeter. So it's very, very what? Very, very simple. So just follow my steps and you will get your answer. If you encounter any other question like this, you can solve it this way. So one thing you must notice that it's not every time that you just see one force acting at one end. Sometimes it may be more than one force at one particular end. So what you do is that if it's more than one force at one particular end, remember what the principle of moment said. He said the sum of clockwise moments. The sum of clockwise moments. So what you do is that you add the sum of the moments on one side. You get, you add it. So if you have more than one, you will get the moment of each of them and now add it. The one on the anti-clockwise side and the one on the clockwise side, you will add them and you will equate them and you do it in one way. So maybe we'll take a question on that and we'll call it a video, a wrap.